There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to continue our new direction of physics videos. This is video 12. We're back into the self-interacting field theory. Okay. Compared with previous videos, we were talking about self-interacting Newton's law of gravity. Now we're going to talk about self-interacting general relativity. Okay. So we're going to see Einstein's field equations. In the previous video, in order for us to complete our self-interacting field theory, we need to modify to revisit quantum mechanics because we have some infinities we need to get rid of. So that's a previous video. We already did that. Okay. So in the conclusion, it's quantum mechanics, Fenster geometry, complex Fenster geometry. We also showed that the self-interacting field theory also have a scalar factor which need to bring into Einstein's field equations. And we also see that in the previous video, two videos, we see that we can bring a scaling factor into the quantum mechanics. That scaling factor is able to remove infinities. Okay. So this video we're going to talk about, we're going to rewrite Einstein's field equation into a format which it's like a self-interacting field theory part. Okay, we're going to write into the self-interacting format. Format will be like electromagnetism. Because Einstein's field equation is not a tensor, it has some conflict of doesn't have the self-interacting scalar part. We want to bring that, okay? So hopefully we'll find the solutions of strong interaction, quantum interaction, and gravitation in the same equation, okay? That's what we hope to do. So the field equation in general relativity, that's Einstein's general relativity. You have a curvature tensor and contract curvature tensor times the metric tensor, okay? So this is the affine connection part, okay, derivative of that. So if we rewrite the Ricci tensor, okay, we see that that's our scalar, okay? This is the tensor part, okay? This is the tensor self-interaction, tensor nonlinear, okay? Nonlinear part, okay? Okay, so that's the Einstein's geodesic equation doesn't have this term, okay? Doesn't have this term, okay? That's Einstein's geodesic equation. Einstein always say, okay, let's redefine the d tau, okay, or dt, okay, the variables. Then can eliminate that. So that's Einstein's geodesic equation, always eliminate that, okay? But now we would like to bring it back, okay? Because our scaling factor is part of the equation we need to match the self-interacting field theory with quantum mechanics. So we need to bring this back, okay? So now, because Einstein's affine connection is not a tensor, we redefine that this tensor became affine connection. Einstein's affine connection became, I want to basically define a new tensor, ijk equals d ijk plus gamma ijk, like that, okay? So this is the Minkowski spacetime Christoffel symbol, okay? This is a difference tensor, okay? The difference tensor is related to gravitation. The Minkowski part, this is our coordinate change. So Einstein's field equation put the affine connection, basically the coordinate change, the space part, and the relate to mass. This is related to the mass, okay? Together. They put together on me. Then it became a long tensor. I don't think it's a good idea. Let's separate that to see what we got, okay? So what we got, I mean, in the paper, I put it in the ResearchGate. We proved that this is a tensor, okay? Basically, the difference tensor is a tensor, okay? So we can rewrite the Ricci tensor like that, okay? Okay, and the extra part, it's Minkowski space, okay? Minkowski, okay, space, okay? Because it's a flat space, okay? Minkowski space, it's a flat space. This equals 0, okay? So now when we define a difference tensor to replace Einstein's affine connections, we see that the Ricci tensor is a tensor, okay, plus something equal 0. Okay, so that means we kicked out the space part, because when we have normal coordinate, we have x, y, z, okay, x, y, z, or t, or plus that, okay, we have that. Now if we convert it into the spherical coordinate, we have t, r, theta, and phi, okay, that's what we call space part. This coordinate transformation, that's a Minkowski transformation part. We just put this part. I mean, in some cases, this is not 0, but the curvature part is 0. But this affine connection may not be 0, okay, of the Minkowski space may not be 0. That means the gamma ijk, it's not all equal 0, okay? So we have the affine connection ijk equals dijk, okay, plus this. This may not be 0, but the curvature part is 0, okay? So now that means we can write Ricci tensor, Einstein's tensor part into a tensor, and plus a 0. Let's kick away this 0. But this we cannot, because the affine connection, you still have the this part, the affine connection of the Minkowski space. That means when we change this coordinate to this coordinate, they're not 0. But if we see the Einstein's field equation, if we submit into that, we will see something interesting, okay? So after we define the curvature tensor, difference tensor, we can remove this. This is very interesting, okay? This is the long linear term. Okay, this is the divergence. Okay, so we see that Einstein's Ricci tensor can now become a divergent plus a long linear term. We will prove that this nonlinear term is a self-interacting field. Okay, so the divergent term is the energy momentum divergency, the difference tensor divergency term. Okay, but this term will be very close to the electroweak or Maxwell equation, except now we have a long linear term. So the beauty of the difference tensor, I want to just forget forget the affine connection of the Minkowski space. It's just a mathematics, okay? For physics, let's define the difference tensors of affine connection of the Einstein's part minus the Minkowski space. If we define that, okay, but we have extra term here, okay? So what's interesting that if you write out this, you will see that this term, I said may not be zero, but it can be absorbed into the metric tensor derivative. Okay, in the Minkowski spacetime. That means we redefined that the difference tensor is a tensor in the flat space or Minkowski space. Okay. So now when you change coordinate, it's fine. Okay. The difference tensor, you just differentiate the metric tensor in the curved spacetime. That means if you change from x, y, z coordinate, okay, t, x, y coordinate to t, r, theta, phi, you just replace the derivative of this partial g mu theta partial x by a derivative in this curved spacetime. Okay, so that means it is a tensor. That means when Einstein defined g mu nu as tensor in the curved spacetime, okay, this is a tensor in the curved spacetime defined by, okay, by this affine connection. Now we see that g mu nu, the matrix tensor, it's a tensor in the spacetime of curved space or flat space. Both coordinates, they are tensor. Okay, so then this gives the difference tensor a beauty property. Okay, very beauty property. Also, what we see that the contract, we contract the upper index and lower index. We see this. Okay, the reason I like this is a Jacobian of the g mu nu to eta mu nu. Okay, that's the two space time, flat space time to a curved space time. They have a Jacobian. So this is what I call scaling factor. Okay, so that means by defining the difference tensor, we see that the Ricci tensor can be derived like that, can be expressed in a curved coordinate. You have self-interacting term plus a divergent term. And then when you expand this like that, this became a tensor. This is a scalar. It's a scaling factor I designed, okay, because it's related to d tau. Okay, so this is where it's equal 0 at Schwarzschild solutions. So I'm lucky, yeah. So when I define a difference tensor, we see it's a tensor, okay? That's good. So now general relativity became a tensor plus a scalar, okay? Instead of very complicated or ugly affine connections. I'm the first person proposed this difference tensor to remove the flat space-time out of Einstein's field equation, okay? I removed that and also proved that this difference tensor is a tensor in our Minkowski spacetime, whatever coordinate you change. It's because this property. And also the beauty that this is, we found a scalar factor, it's between the different Lagrangians. That's a Jacobian, okay? So now Einstein's field equation have a tensor plus a scalar. The scalar is a Jacobian, okay? Between the two spacetime, the flat spacetime and the curved spacetime, there's a Jacobian, okay? So, and I don't need to worry about general relativity test because all general relativity test is in the Schwarzschild solution, okay? And that this term equals 0. So whatever I add, this extra term doesn't matter, okay? Doesn't change general relativity classic test, okay? So now what we see that the geodesic equation became the acceleration caused by coordinate, the acceleration caused by mass or gravity, okay, or strong interaction or whatever other interaction. Let's call this self-interaction, okay? And then we have another term, that's a scalar part, where Einstein on purposely eliminated, okay? I bring it back, okay? So, but these two forces, these two part of the forces will be my self-interacting forces, okay? So these two forces combination became the new modified general relativity. This is why it's good, because we separated the geometry part caused by the geometry when we change our coordinate from the gravitation can be caused by mass. Now if you go back to the Schwarzschild solution, you will see this related to mass. In the next video, we're going to talk about the tensor version of the self-interacting field theory. It's a new format of the general relativity, which compatible to the electroweak interaction. So even now we have a difference tensor. We're going to introduce another tensor. We'll also call it F, okay? What's interesting in this previous separation, we separate the geometry from the mass, okay, which we call gravitation, okay. We separate that from the geometry part. That will make the equation describe energy momentum, which causing the space-time to change, okay? But not our coordinate we're defining, okay? That will make the equation more elegant compared with Einstein's general relativity, okay? Thank you.